Black holes might not truly have an inside. I know how that sounds. It sounds like we're throwing out Einstein or claiming there's a literal wall at the event horizon. That's not what we mean. What we mean is subtler, and honestly more unsettling in a complete theory of quantum gravity. The black hole interior may not be a separate place where new, independent information is stored. The inside could be a derived description, something that emerges when you organize the physics in the right way. And in a minute, we'll hit the clue that forces this conversation. A black hole's entropy, its information capacity scales with surface area, not volume. If that's true, then our usual mental picture of space inside a sphere may be the wrong starting point. So let's slow down and define the claim carefully. When we say black holes have no interior, we do not mean you bounce off the horizon like it's a solid shell. We do not mean nothing can fall in. And we do not mean general relativity is useless. In classical general relativity, a black hole very much has an interior region. Cross the horizon and, according to Einstein's equations, the geometry continues. There's more spacetime in there. The claim often associated with ideas pushed by physicists like Leonard Susskind is about what's fundamental versus what's emergent. The interior may be real in the same sense that many everyday things are real. Real as a stable, predictive description, but not the deepest layer of the universe's bookkeeping. If that sounds like philosophy, good, because physics, at the edges, becomes extremely picky about what real means. Here's an analogy that will matter later: temperature. Temperature feels like a basic property of the world. You measure it, you react to it, you can't ignore it. But temperature isn't a microscopic object. No one has ever found a temperature particle. Temperature is a summary, a macroscopic variable that emerges from countless molecules moving and colliding. It's real, but it's not fundamental. Or take the icons on your phone. When you drag a file into a folder, it feels like you moved an object into a container. Under the hood, you change patterns of electrical states. The folder isn't fake, your computer's behavior is reliably organized around it, but it's not the lowest level description of what's happening. Keep those examples in your pocket, because the open question is this: could spacetime itself sometimes behave like that? Not imaginary, just not the bottom layer. Now for a quick mental experiment. Imagine you walk into a museum with a strict rule. You're not allowed to go inside the galleries. You can only stand in the hallway that wraps around the exhibits, but the museum staff hands you a perfect, complete catalog describing every painting, every sculpture, every placement, every lighting condition, everything. If the catalog is truly complete, then in principle you could reconstruct the entire interior experience without ever stepping inside. So what would inside mean in that case? It would still be a meaningful concept for visitors, but at the deepest level, the information would already be captured at the boundary. That's the kind of possibility black hole physics starts to hint at, because black holes aren't just gravity, they're where gravity collides with quantum mechanics. In quantum physics, there's a core expectation, one that's held up incredibly well, that information is not destroyed. You can scramble it, you can spread it out, you can hide it in complex correlations. But the underlying evolution for an isolated system keeps the total information intact. Classical physics is more casual. Burn a book, and in a sense the story is gone. The ashes don't contain the novel in any practical way. Now place a book near a black hole. From the outside, it looks like the book falls toward the horizon, slows down, dims, and fades. From the book's point of view, it crosses the horizon in finite time and continues inward. Two perspectives, already a little strange but manageable. Then Stephen Hawking added a new ingredient: black holes are not perfectly black. Quantum effects allow them to emit radiation. Over immense timescales, they can evaporate. And that creates the famous problem: if the black hole eventually evaporates away, what happened to the information and everything that fell in? Does it disappear from the universe? If yes, quantum theory seems to break. If no, then where was the information stored? And how did it get out? Hold that question. We're going to return to it. But first we need one number, a number that changes everything. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes behave like they have entropy. Entropy is roughly a measure of how many microscopic configurations correspond to the same macroscopic appearance. If two objects look identical from the outside, but they could be built from many different microarrangements, the entropy counts those possibilities. Here's the shock. A black hole's entropy is proportional to the area of its event horizon, not the volume inside. The area, if you're used to ordinary objects, that is backwards. For normal matter, the number of ways to arrange the stuff inside scales with volume. In bigger box, more room, more microstates. But black holes seem to max out. They're like the densest possible storage devices nature allows, and the storage limit scales like the skin. So ask the uncomfortable question. If the information capacity scales with area, is the inside actually where the information lives, or is the horizon doing the accounting? This is where the phrase holographic principle enters. A hologram is a 2D surface that can encode a 3D image. The holographic principle in physics is the idea that a region of space might be fully describable by data living on its boundary. The boundary doesn't just surround the region. In a deep sense, it may contain the complete description. Now, to be clear, holographic does not mean fake. It doesn't mean we live in a cheap projection. It means the fundamental degrees of freedom, the independent bits of reality may scale like area, and a boundary-based description might be complete. So return to the black hole. If the horizon carries the bookkeeping, then the black hole interior might not be an independent vault of information. The interior could be something we reconstruct, something emergent when we translate the boundary data into a space-time story. At this point, a reasonable person asks, is this just a metaphor, or is it actually true somewhere in physics? There is one setting where we have an extremely strong proof of concept. It's called AdCFT, proposed by Juan Maldacena. Here's the intuition. AdCFT says that a theory with gravity living in a bulk spacetime can be equivalent to a quantum theory without gravity living on the boundary of that spacetime. Two very different languages. One was gravity and extraspatial depth. One without yet, they describe the same physics. In that framework, bulk objects, including black holes, have a complete description in the boundary theory. In other words, the boundary is not merely a shadow. It's the full story, written in a different code. Now, the important limitation, our universe is not exactly the kind of space-time used in the cleanest versions of AdCFT. So we cannot honestly say, this proves our universe is holographic in a direct way. But it does prove something profound. It is possible for a lower dimensional, non-gravitational quantum system to encode an entire higher dimensional gravitational world, including what feels like interior space. So when someone says maybe black holes have no interior, one careful translation is the fundamental description may live on degrees of freedom associated with the boundary, and the interior spacetime is a derived concept. Now we can come back to the information paradox. Here's the intuition with no equations. It claims that a theory with gravity living in a certain kind of space-time and ad space can be exactly equivalent to a quantum theory with no gravity living on the boundary of that space. Two descriptions, two different languages, same underlying physics. In one language, you have a higher dimensional world with curved space-time, black holes, and gravity as geometry. In the other language, you have a lower dimensional quantum system, no gravity, just particles and fields interacting according to quantum rules. And yet, remarkably, these are not two different worlds. They are two ways of describing the same world. If that's true, then at least in that setting, space is not fundamental, because the bulk gravitational space can be reconstructed from the boundary quantum theory. The extra dimension behaves like an emergent direction, something you infer from patterns in the more fundamental description. Now we need to be honest about scope. Our universe does not appear to be exactly the kind of space used in the simplest AdCFT examples. On cosmic scales, we observe accelerated expansion consistent with a positive cosmological constant, which is different geometry. So AdCFT is not a finished explanation of everything, but it is a proof of concept of something radical. Gravity and geometry can emerge from a non-gravitational quantum system. Space-time can be an output, and that returns us to another open loop. If space can be emergent, what about time? Because time feels even more basic than space. We can imagine an empty region of space. It's much harder to imagine no time, because imagining itself feels like a process. So let's switch questions. Instead of asking, what is space made of? Ask, what does space do? In everyday physics, space provides distances near, far, inside, outside. It organizes interactions, causes, and signals. Now consider a different primitive, relationships. In quantum mechanics, one of the deepest kinds of relationship is entanglement correlations that cannot be reduced to independent properties of separate parts. Entanglement is not just hidden communication. It's a structure of the joint system. Two subsystems can be so linked that describing one without the other loses essential information. Over the last few decades, a growing set of ideas has suggested that the pattern of entanglement in a quantum system can behave like a blueprint for geometry. Here's a way to picture it. Imagine the universe at the deepest level as a vast network of quantum degrees of freedom. Think of them like nodes. And between nodes, there are links representing correlations, how strongly the states depend on each other. If correlations are mostly local, each node strongly linked to a limited neighborhood, then an emergent sense of nearby can arise, not because space was assumed, but because the network behaves as if proximity exists. Distance, in this view, is not a primitive ruler laid across reality. Distance is a way of summarizing connectivity. Change the pattern of entanglement, and you can change the emergent geometry like tightening or loosening threads in a woven fabric. Some approaches visualize this using tensor networks, where geometry-like shapes appear naturally from how information is organized. Other proposals connect entanglement to space-time connections in more speculative ways. You might hear phrases like air equals epper, suggesting a link between entanglement and wormhole-like connections. That idea is intriguing and actively explored, but it sits closer to the frontier than to settled textbook physics. So let's draw a careful line. It is well established that black holes have entropy proportional to horizon area, and that holographic ideas are deeply connected to quantum gravity. It is well established that AdCFT provides exact examples where a gravitational spacetime emerges from a non-gravitational quantum theory. It is strongly suggested, but still an area of research, exactly how general this is, that spacetime geometry, in broader contexts, is controlled by information-theoretic structure, including entanglement. And it is more speculative to claim we have a complete universal account of emergent time in our actual universe. But even that speculation has a disciplined motivation. If space is emergent from relationships, then time might be connected to how those relationships update, how information flows, how one description coarse grains into another, or how an observer embedded in the system experiences change. In some models, what we call time may be tied to a kind of bookkeeping of quantum complexity, how difficult it is to transform one state into another using basic operations. In other approaches, time may emerge as a parameter inside an effective description, not present in the deepest formulation. These are research-level ideas, not final answers. Still, we can say something solid. Physics has repeatedly shown that concepts we treat as primary can turn out to be derived. So the idea of emergent time is not absurd on its face. It's an open question with serious motivation. Now we can close our earlier question. If space isn't fundamental, where are we? We are still in the world. We still live among objects, distances, and durations. But where may be a relational question, not a container question. A location could be like a coordinate in a model, extremely useful, highly reliable, but not the deepest thing in the story. And that brings us to why any of this matters beyond intellectual thrill. Because if space-time is emergent, it changes how we interpret limits, beginnings, and what it means for something to be real. Here are three implications. First, the universe may have a fundamental information limit. The area scaling entropy of black holes suggests that in a world with gravity, you can't pack unlimited information into a region. There is a cap, and that cap scales like boundary area. That hints that spacetime cannot be infinitely divisible in the naive way we imagine. Not necessarily that there's a simple pixel size you can point to, but that how much can happen in a region has a deep constraint. Second, the Big Bang might be less like a location in time and more like a breakdown of the spacetime description. When people ask, what happened before the Big Bang? They're treating time as a fundamental coordinate that extends beyond the beginning. But if time is emergent, then before time might be like asking, what's north of the North Pole? It might not be a meaningful question inside the derived description. That doesn't solve cosmology. It doesn't magically explain the origin of the universe, but it reframes the puzzle. It suggests we may need a deeper language in spacetime to even state the question properly. And third, emergent does not mean meaningless. A table is real, even if at the atomic level it's mostly empty space and electromagnetic forces. A wave is real, even if it's made of many particles moving together. A hurricane is real, even though it's not a fundamental particle. Reality comes in layers. Space-time, in this view, is one of the most robust layers we've ever discovered, so robust that it feels like the foundation, but it might be the result of a deeper organization of information. Now let's gather the thread from start to finish. We began with a claim that sounds impossible. Space and time may not be fundamental. We clarified what that means. Not that the world is fake, but that space-time could be like temperature, a derived description that emerges when you look at the right scale and the right collective behavior. Then, black holes force the issue. They create an information problem. If black holes evaporate, does information vanish? The prevailing view says no information is preserved, but the way it's preserved pushes us toward a new kind of bookkeeping. Black holes also gave us the area law, entropy scaling with the area of the horizon, not the volume inside. That clue points naturally to holography, the possibility that the boundary encodes the interior. And AdCF that shows this idea can be exact in certain model universes, an explicit case where a gravitational spacetime emerges from a lower dimensional quantum theory without gravity. From there, we explored the emergence map, the possibility that geometry is stitched together by quantum relationships like entanglement, and that time might be connected to deeper notions of information flow, though the full story for our universe remains incomplete and actively researched. So here's the core takeaway. Space and time might be the universe's output, not its input, and that makes them no less real. It makes them more interesting because it suggests they are telling us something about the deeper architecture underneath. If you want more slow, conceptual physics documentaries like this, no equations, just intuition, and the best honest picture we can draw, subscribe. And here's a question to leave in the comments, because it cuts right to the heart of it. If spacetime emerges from information and relationships, what do you think is truly fundamental, the stuff of reality or the structure connecting it?